Autophagy plays a central role in maintaining insulin sensitivity, acting as a cellular quality control system that ensures the smooth functioning of insulin signaling pathways. When autophagy is operating correctly, it clears out damaged mitochondria, misfolded proteins, and lipid droplets that might otherwise interfere with the body's ability to respond effectively to insulin. This internal cleansing mechanism is particularly important in insulin-sensitive tissues such as skeletal muscle, liver, and adipose tissue. In lean individuals or those with balanced metabolic states, autophagy helps preserve insulin receptor function by preventing the accumulation of cellular stressors that can block insulin signaling. For example, the removal of dysfunctional mitochondria through mitophagy reduces the generation of reactive oxygen species, ROS, which are known to impair insulin action by damaging key signaling molecules. Autophagy also assists in lipid turnover, preventing excess fat from accumulating inside cells where it can disrupt glucose uptake and metabolism. However, in obesity, this protective system often falters. Studies consistently show that obese individuals experience impaired autophagy, especially in metabolic organs. When autophagic flux is suppressed, dysfunctional mitochondria and toxic lipid intermediates accumulate. These cellular pollutants activate stress pathways such as JNK and IKK, which directly inhibit insulin receptor substrates and block downstream signaling. The result is insulin resistance, a hallmark of metabolic disease, where cells no longer respond adequately to insulin, forcing the pancreas to produce more and eventually leading to hyperinsulinemia and possibly type 2 diabetes. Insulin resistance doesn't just affect blood sugar control, it amplifies fat storage, increases inflammation, and contributes to a range of systemic health problems. And yet, impaired autophagy remains an underappreciated root cause of this cascade. It's not just that the body gains weight and then develops insulin resistance. Rather, the breakdown of autophagy appears to be an early and active driver of these dysfunctions. Despite the gravity of this issue, there is room for optimism. Research suggests that enhancing autophagy through means such as intermittent fasting, exercise, and certain natural compounds like spermidine or resveratrol can help restore insulin sensitivity. These interventions promote the removal of cellular debris and normalize mitochondrial function, allowing insulin signaling to recover. Early trials in both animals and humans have shown promising results: improved glucose uptake in muscles, better liver function, and reduced inflammation across tissues. Still, a warning is necessary. While boosting autophagy can improve insulin sensitivity, overactivation in the wrong context or for extended periods may have adverse effects. In extreme cases, excessive autophagy could contribute to muscle wasting or impair immune function. Therefore, the goal is not simply more autophagy, but rather balanced autophagy, regulated according to physiological needs and tailored to individual health status. In summary, autophagy is more than a cellular cleanup process. It is a gatekeeper of insulin responsiveness and metabolic stability. Its impairment in obesity sets off a chain reaction that culminates in widespread insulin resistance. Yet, by restoring healthy autophagic function, we may find one of the most effective and natural routes to reversing this dysfunction. Properly modulated, autophagy could be a cornerstone of future treatments aimed at not just controlling blood sugar, but rebuilding metabolic resilience from the cellular level up.